So hi everyone, I'm Mingjia. I'm a first year PhD student here at DAMP in the soft matter group. So today I will be talking about a geometric field theory for elastohydrodynamics of Cosserat. This is based on a joint work with my brilliant colleagues Mohammed and Balash, as well as my amazing supervisor Ronald Dway, who is also here today. So what exactly is a Cosserat and why do we even care about it? Well, a Cosserat is a 1D flexible cylinder structure that can stretch, shear, twist, and bend, having 6 local deformation modes and, of course, an infinite number of degrees of freedom. And as you can see from the pictures, they are literally everywhere. So I found one literally when I was making the slides while I was trying to untangle my twisted earphones. So they are everywhere. And so in our formulation, we start with these vectorial expressions of our equations of motion. However, this does not really tell us the underlying geometry. So we go one step further to resolve all the quantities into the moving frame, which is just a set of orthonormal basis vectors that move along the rod, just like being on the roller coaster. And the components of the moving frame vectors tell us exactly what the spatial symmetry is. And then using this symmetry, we take one step further to recognize the important geometric structure in our system, which is a Lie group. And then we can write our equations on this Lie group, and the geometric field theory that we formulate will give us coordinate-independent equations of motion. So the geometric insight of the Cosserat is that each cross-section's configuration phi is an element of this matrix Lie group SE3, characterizing all three-dimensional rigid transformations. So essentially, it's just like a 4x4 matrix where the R is the centerline position and the E1, E2, E3 are the moving frame vectors. And the kinematic equations, for example, can be written as these matrix-valued Lie group PDEs, where E is the strain/deformation and V is the velocity. And the geometric field theory provides a unified framework for us to cast our equations into these geometric forms, where the last geometrized equation contains all the important information, where we express our velocity V as a function of the configuration map phi once we are in this overdamped regime. And we can also apply our methodology to construct a structure-preserving numerical integration scheme. And I guess you probably guessed the name from the program, yes, using spectral methods. And we are also exploring applications in actuated motions of the Cosserat. So this is an animation that I made a few months ago showing the centerline motions of a two-dimensional Cosserat with a nonlinear clamp-free boundary conditions. So the take-home message is that we have developed this coordinate-free, geometrically exact field theory to model the nonlinear rod motions in a viscous fluid using structure-preserving numerical scheme and with possible applications in actuation of soft robotics. So our framework is based on this work by Lucas in his paper Cartan Medium, which was 2 years ago. And again, I want to thank my colleagues, my supervisor, and also thank you to everyone here. I'm going to wrap it up here. I also do have a post outside, so feel free to ask me any questions and I'll be able to have a chat.